Hi, welcome back. Last time we discussed the rather long and detailed history of how were the individual subatomic particles discovered. Matter is made of atoms, and that's actually where we began last time. The idea from Greek philosophy in the 2,500 years ago of, well, we don't know what things are made of, but we're going to assume that they're made of individual particles, and we're going to call those atoms, or atomos, or whatever the word they actually used was. And then we learned about John Dalton, who discovered many true things. They weren't necessarily 100% accurate, but they were like 90 to 99% accurate about the nature of the atoms that make up everyday substances and compounds as well. And then we got into the history of the proton, the neutron, and the electron, which are really the only things that we need to worry about that make up atoms. Protons and neutrons are made of quarks themselves. Up, down, strange, charm. There's a few other quarks, I think. We are definitely not worrying about those for the purposes of this class. But we will have a short lesson today on we know, okay, so really all we've defined so far is the things that make up atoms. Now, how do we distinguish between the different atoms, as you can see by the title here? So, all matter in the universe is made of protons, neutrons, and electrons, and thanks to J.J. Thomson's experiment first demonstrated this. All electrons are exactly the same. In his case, he found that the mass-to-charge ratio was always identical, no matter what he looked at. So I can take two different atoms or elements, phosphorus and sulfur or whatever, and I can swap one or two or three of the protons from one atom to the next. Something like that really isn't doable. But if you could do it, nothing would change. The atoms, elements themselves would remain fundamentally the same. Similarly, this actually happens with chemical bonding, covalent bonding especially, because it shares electrons. We can exchange electrons through covalent or ionic bonding, and the identity of the element still remains. It's the same. So the point is, all protons in the universe are exactly the same, all neutrons in the universe are exactly the same, and all electrons are. So what is the difference from one element or one atom to the next? Well, in the strictest terms, the definition of an atom or element is really the number of protons. So that is its atomic number. Wherever an element falls on the periodic table, that is its atomic number. That is how many protons that atom/element has, and that is the only number it possibly can be. So for example, oxygen has its atomic number is 8. It has 8 protons. That's it. No other element can have 8 protons and not be oxygen. And for gold, it is 79 protons. If you took an element, like a heavy element, and you removed all of the neutrons away from it, gold has about 120 neutrons in it. If you removed every single neutron, by our definition, it would still be gold. Now, that's not really doable, and the nucleus would actually decay and fly apart because the protons are positively charged, and they repel each other. So there's this thing called the strong nuclear force that holds the nuclei of atoms together. Again, we're not going to get into detail with that, but technically speaking, it's really just the atomic number that matters. There's only one element that doesn't have neutrons, and that's hydrogen. Although hydrogen can have neutrons. We'll get into that in a little bit. I already said this, but wherever an element lies on the periodic table, that's how you find out its atomic number. So I don't know which element this is supposed to be. I think I used this picture for francium in the last one, so maybe that's what it is. But it's just made of protons, neutrons, and electrons. And count the number of protons, that is what element you're dealing with. So when it comes to like studying matter and the physical properties of matter too, For example, mass, density, weight, all that stuff. That is determined by the number of protons and neutrons. If I took any object and I removed all of the electrons from it, 99.9995% of its mass would remain. Now the material would be like completely altered because it would have no electrons. It'd be very bizarre, exotic type of matter, but virtually all of its mass would still be there. So the number of protons and neutrons is significant. We call that atomic mass, or the mass number. Now, you see atomic mass on the periodic table, but it's what we call the average atomic mass. We'll get into that in a second. So oftentimes you have to, when you're explaining an element, you want to, especially for heavy elements, you want to give its mass number. So we would say gold 197. So gold 197, gold always has 79 protons. So we can actually figure out how many neutrons it has. Just do the math. In this case, it would be 118 neutrons. But 197, that is its mass number. That's its atomic mass. And we can derive how many protons and neutrons it has from that as well. Now, the reason we have to be specific is because the vast majority, I don't know exactly as a percentage, but the majority of elements actually come in different varieties. They'll have different masses and then therefore different densities, because the number of neutrons does not determine what type of element it is. So these things called isotopes are versions of the same atom, the same element, but with different numbers of neutrons. So we distinguish them by using the atomic mass. So for example, there's carbon-12. Carbon is number 6 on the periodic table, so it always has 6 protons. Carbon-12 is carbon with 6 protons and then therefore 6 neutrons as well. Carbon-14 is carbon with, it always has 6 protons, like I said, but then it has 8 neutrons in that case. So we have to be specific on this when adding things up and when trying to account for mass and things like that. And we will have practice with that in this class. An upcoming lab that we will do will be making our own isotopes out of pennies, and then tracking we're going to be calculating the average atomic mass. Now, if we look at carbon on the periodic table, carbon, its atomic number is 6, and so on the periodic table, it'll always just say 6. Now, the atomic mass will be written below that, but that is not a whole number. It's never a whole number for pretty much any element. So for carbon, it is 12.001. Now, what does that mean? It's the average atomic mass. So the majority, by far, the vast majority of carbon atoms in the universe that we detect are carbon-12. So there are 6 protons, 6 neutrons. But these carbon-13 and carbon-14 isotopes, they exist too. And when you account for those, let's just say if you had the number 12, let's say you had 100, you took 12 plus 12 100 times, and then you divide by 100. What's the answer? Well, it's 12. But 12 plus 12, do that 100 times, and then do plus 13 divided by 101. That's not an even number anymore. That's not 12 anymore. So it's very slightly higher than that. That's why the mass number on your periodic table is not a whole number. It's an average of all atomic masses in the proportion that we find them in the universe. That's the key thing. So for example, let's just say we have carbon 12, 13, 14. The average atomic mass of carbon is not the average of 12, 13, and 14, because that would be 13. That's not what we have on the periodic table. Instead, the number is really close to 12 because it takes into account the percentages, how common each isotope is. Let's say it that way. Here are the different, here's a visualization of the different carbon atoms. So there you have it. Now, I guess I got ahead of myself here. So, and this one, it's a little more specific. Different periodic tables their decimal goes to different places. So this is maybe the official one, 12.0107. And that's called an atomic mass unit. An atomic mass unit is protons and neutrons have the same mass. Like, they're so close to each other that we can just say that they're identical. So an atomic mass unit is the mass of one proton or neutron, because they're virtually identical. So the 12 here in carbon just means a total number of 12 subatomic particles, at least protons or neutrons. And that's really, I know that was really short and sweet and simple, but the differences between elements are really subtle. The only difference, said it a dozen times now, the only difference between gold and mercury is one proton, right? So that's all we have to account for. And then the isotopes are a little tricky, but I think we've spelled it out pretty well here. In the next lesson, we're going to talk a little bit more specifically about the kind of math that we do in chemistry, and how to calculate things, and talk about experimental error and experimental range and things like that. So, thank you for watching.